All right. Well, it's 2 o'clock, so I think we should go ahead and get started. So welcome everybody to our Wednesday seminar. Today I'm excited to introduce Andrew Dye. So Andrew joined us in August as a postdoctoral researcher in the NOvA and Dune group, and he's currently the production convener for NOvA. He's working on neutrino oscillation analyses. He is also in the Dune Computing Consortium working on all kinds of interesting computational solutions for the Dune project. Andrew has got his undergraduate degree from Georgia Southern University and recently completed his PhD on the topic that he's going to be telling us about today, on profiled Feldman-Cousins methods for confidence interval construction in NOvA from the University of Mississippi. And so without further ado, help me in welcoming Andrew.
Thank you. Get this set up without feedback. Check. Good. All right. So, like he said, my name's Andrew Dye. I am going to be talking about the profiled Feldman-Cousins method for confidence interval construction on the NOvA 3 flavor analysis. It is a mouthful. Feldman-Cousins will be FC from now on. All right. So first off, we're going to start talking about neutrinos. Just a brief refresher. So the properties of neutrinos: they are neutral charge, which means they don't interact with the electromagnetic force. They are leptons, so there's no strong force interaction. And they are very, very light, so there's almost no gravitational interaction. And so that basically makes them very hard to detect. And another little bit of a refresher, we're going to talk about eigenstates. So particles can be represented as linear combinations of eigenstates. This is Schrodinger's cat. So the cat is either alive or dead. And so the coefficients attached to these states correspond to the probability of observing the particle in that state. So you can see the probability of it being alive is alpha squared, or beta squared to be dead. And the important thing for quantum mechanics is that eigenstates have to be linearly independent, which means they can't both be alive and dead at the same time. So, as a lepton, the neutrino has two types of eigenstates. There are flavor eigenstates, which are denoted as the electron, muon, and tauon neutrino, and the mass eigenstate, which is just mass 1, 2, and 3. And so for the charged leptons, so the actual electron, muon, and tauon, the mass states are equal to the flavor states. And for neutrinos, that is not true. So neutrinos neutrinos are created as a definite flavor. And then they travel as the superpositions of the mass eigenstates, since that the flavors are a linear combination of the mass eigenstates, which is the next slide. And then upon the interaction at the final state, the flavor is dependent upon the probability amplitudes attached to the mass eigenstates. And so so this little diagram shows you kind of how the mass eigenstates make up the flavor eigenstates. And the matrix that relates these two bases is called the PM&S matrix. PM&S stands for a lot of names that I can't remember off the top of my head, but it's very important. So the PM&S matrix has four primary parameters. So it has the three mixing angles between the three different states, and then one CP violating phase. And you can represent it a lot of different ways. Typically, though, you can see it as a rotation, or three different rotation matrices multiplied together. And so the big open questions in neutrino science is CP violation. So do neutrinos and antineutrinos oscillate differently And if they do, by how much? That's what delta CP measures. So mass hierarchy is, so we can't actually measure the mass of the mass states directly. We can only measure their square differences. And so we actually don't know the difference between the third and the second state and whether or not it's positive or negative, I guess is the best way to put it. We don't know the sign of it. And so that's called the mass hierarchy problem. And so it can either be normal or inverted. And then, of course, what are the oscillation parameters is the other open question. So we measure the actual theta 1, 2, 2, 3, and delta CP. And NOvA is up there at the top because we just, I think, took the record on the best delta M squared 3, 2 measurement in this analysis, actually. So let's talk about NOvA. So the NOvA experiment stands for the NUMI off-axis neutrino appearance experiment. It's a long baseline, high energy experiment which studies neutrino oscillations. And long baseline means that the beam starts at Fermilab and it travels 810 kilometers to Minnesota. NUMI is neutrinos at the main injector, which is a roughly 900 kilowatt beam at Fermilab. And there's two major modes of operation. We have the forward horn current, which produces neutrinos, and then a reverse horn, which produces antineutrinos. And the off-axis part is because we actually aimed we positioned our detector 14.6 millirads off center to basically isolate this 2 GeV neutrino flux, because that is the energy that the NUMI beam produces where the oscillation happens, or it's actually, this is a better way to show it. So this is a simplified version of the probability of appearance of or oscillation from a neutrino electron to a muon, or sorry, a muon neutrino to an electron neutrino over the 810, and you can see the 2 GeV, 810 kilometers puts us right almost on that big band, which is the biggest. It gives us the biggest probability of seeing what we want to see. So the detectors themselves, there's two of them. There's the near detector at Fermilab and a very, very large detector in Minnesota. So other than their size, they are functionally identical. So they are alternating planes of PVC cell filled with like mineral oil. So it's a liquid scintillator that when when a charged particle passes through it, it emits light. That light is then caught by wavelength shifting fibers, which then carries it to a bunch of computer stuff, converts it to signal, and that's the data that we measure. And so, talking about the data. So first off, what are the goals of the 2024 analysis? Well, it's the determination of the atmospheric neutrino mixing parameter, which is theta 2,3, although technically we measure sine squared theta 2,3. And so we also want to find the mass difference of delta M squared 3,2 and the charge parity violating phase, and of course the sign of the mass ordering. And so we used constraints on theta 1,3 from the Diabet experiment. We actually used two different constraints. We'll get more into that a little bit later, but they basically have a 1D and 2D constraint on theta 1,3 and theta 1,3 and delta M squared 3,2 that we used at a certain point. And then we also did, for this analysis, we did a frequentist analysis, which is what I'm going to talk about because it's what I worked on. And then there was a Bayesian analysis done as well, which we did agree. So, all right. So in this analysis, we had multiple samples. So we had two signal channels. So we had the muon neutrino disappearance and the electron neutrino appearance. The energy, and then also that's for both forward horn current and reverse horn current. So you get both the neutrino and antineutrino versions of those. And so for the muon for the disappearance channel, you have this quartile binning based on the hadronic energy that is that produces the interaction. And so the lower you have the hadronic energy, you actually get better signal resolution, which is why we get these quartiles. So quartile 1 is the best resolution, with quartile 4 having a higher hadronic energy, which ends up with the worst resolution. And then the electron neutrino appearance is binned with 4 different samples, I guess. So we have the core sample, a peripheral, and for this analysis, we actually included a new low energy sample down here at the very under 1 GeV or under 2 GeV space. And so the last time this 3-flavor analysis was done in 2020, we had 13.6 protons on target, well, times 10 to the 20 protons on target. And then for the antineutrino, we only had 12.5, so they were roughly similar then. But then in 2024, we actually didn't get any more antineutrino beam, but we doubled our neutrino beam exposure. So basically, we ended up with a total of about 40 times 10 to the 20 protons on target, but only about a quarter of that, or a third of that, was the antineutrino mode. And the reason that that's important is because the protons on target tells us our predicted number of events that we expect to see. And this table here is basically our predicted number of events for each channel, and then our actually observed numbers down there at the bottom with the best fit, with our best guess basically above that. And so I'm not going to go through the whole table, but yeah, so this is the results. And so specifically for the frequentists side of things, we discovered through our fits that delta CP in the normal ordering favors not CP violating phases, basically, so 0 and pi. And then in the inverted ordering, delta CP favors the maximal violating phase. And then sine squared theta 2-3 has a preference for the upper octant in both orderings. And then so this is where we used, which I'll get into how I did this in the Feldman-Cousins section. So, but the way we measured the sign of delta m squared 3-2 was we determined the inverted ordering rejection significance. So basically, how hard does our data deny the inverted ordering? And for the 2 constraints we used was diabae reactor 1D, which was just a constraint on sine squared 2 theta 1-3, and reactor 2D actually adds in a second constraint on delta m squared 3-2 from diabae. Or not delta m squared 1-3. I don't remember, but there's a second constraint. And this is our with friends plot that shows the likelihood surface of the sine squared theta 2-3, delta m squared 3-2 in the normal ordering. And it's a comparison with all the other popular experiments. And you can see, we really tightened down our area, and our best fits there in the upper octant of sine squared theta 2-3. And now let's talk about Feldman-Cousins. So the thing I just showed was the likelihood plot. The best fit values that come from likelihood plots are not really sufficient to make inferences about what the value actually is. So the likelihood just tells you how likely you are to observe that point at that spot given the data. And this area around the best fit on the likelihood surface is called a confidence interval. So a confidence interval is a region of your parameter space that encompasses how likely you are to see a specific set of parameters and to a chosen level of confidence. And so you can see this dark blue area we are 68% confident that our parameters, the true parameters, lie within this area. And the 90% confidence is the lighter blue area. So you can see if we want higher confidence, we just make our area bigger because then we're more likely to get the right answer. And so how are confidence intervals calculated? So first off, it requires knowledge about your test statistic. So we specifically use log likelihood ratios. So it's which falls under something known as Wilks theorem. Wilks theorem says the distribution of a log likelihood ratio converges to a chi-squared distribution given certain conditions that we'll get into. And the chi-squared is good because it's very well known, well documented distribution. There are lookup tables. You basically go to a lookup table, you say, this is the confidence level I want, and this is the degrees of freedom, and it tells you the chi-squared value that you need to be at for it to be within that region. So what are the conditions of Wilks theorem? So first thing you need is a large sample size. Again, from the beginning, neutrinos don't interact very much, so they're rare. Luckily, with our new data set, we actually had over 10 years of data. This actually became less of a problem in this analysis than it was in previous analyses. But the nested hypothesis says that your null hypothesis that you're testing has to be a special case of your alternative. So your alternative is, fixed parameters. So measuring parameters under normal or inverted mass ordering is a nested hypothesis because you're assuming normal and then you're determining parameters within that case. But to determine the mass ordering itself, the normal ordering is not a subset of the inverted ordering. So that's actually not a nested hypothesis. Those are two independent hypotheses, so Wilks theorem fails. And then the other thing is you have to have ellipsoidal distributions of uncertainty, which basically just means, so our likelihood should look like a ellipse and not a bean. So that's the other part where Wilks theorem breaks apart. And you can also see here, so this is the nested hypothesis and for stuff. So these are our expected values under inverted ordering, normal ordering, and also upper and lower octant for sine squared theta 2, 3. And then, so that's the degeneracy in our model, basically. So that's the primary mode of failure. And then, so if we assume that our distribution of log likelihood ratios is actually a chi-squared, and we use those values to construct our confidence intervals, it's not correct. And so I basically just explained that. Okay. So, and this is what I mean by not correct. So if your intended coverage is obviously you want perfect coverage, if you use Wilks theorem, you get not what you want. And so we have to use the Feldman-Cousins method to get actual good coverage of our confidence region. And so that's what Feldman-Cousins is it's a method of empirically generating a new chi-squared distribution to use in order to pull your critical values from. And so it was developed by Gary Feldman, Robert Cousins. The concept is that you generate pseudo experiments at every point in your parameter space that you want to correct for. So, for instance, in our 2D plot I showed earlier, we would go to each pair of those parameters and generate a number of pseudo experiments. And so a pseudo experiment is just, it's mock data, it's Monte Carlo, using the model predictions. And then using that pseudo experiment, you fit it. So you determine the log likelihood for each pseudo experiment, which you basically generate then a new distribution. And that critical chi-squared value comes from this new distribution, and you can obtain it by, it's basically the point in the distribution that corresponds to the percent confidence you want to be. And this is kind of how it shows where how it changes the critical chi-squared value. So the red line on these plots is the chi-square distribution. And you can see that the histogram is actually your measured delta chi-squared values for each pseudo experiment. And you can see if it reproduces the chi-squared, you kind of follow that red line. Or it can lower your critical chi-squared value by being, under, or raise it by being over. And so this is kind of how the shifting of the critical chi-squared happens. So the thing with neutrino, with NOvA at least, is that there's like 50 plus parameters technically, because there's the four actual oscillation parameters, but then there's like 30 plus systematics. And so traditional Feldman-Cousins doesn't actually have a way to handle that. If in traditional Feldman-Cousins, we would have had to literally visit every point in our parameter space, including all 50 of those systematics, and that's not feasible. And so NOvA developed this thing called the profiled Feldman-Cousins method, which is a way for us to handle those nuisance parameters. And so a nuisance parameter is any parameter that we're not actively fitting. So the plot I showed earlier was the sine squared theta 2, 3, delta m squared 3, 2. So those are our active parameters. And then the nuisance parameters would be the other two oscillation parameters plus all of our systematic parameters. And so we do what's called profiling over these nuisance parameters, where we basically, when we generate our pseudo experiments at each point, we fix our nuisance parameters to the best fit values, the observed best fit values at that point. And so the profiled values differ for each combination of the parameters of interest. So you basically have a different set of profiled values for every spot in your histogram. And so this coverage accuracy here is taken from our paper, where it shows that you basically don't really lose much accuracy from using this profiled method from doing them all. And this is our frequentist plot, where so this is actually that 2D plot I showed, but I just have a different overlay on it. And so you can see here how Feldman-Cousins affected it. So the red dotted line is the uncorrected plot, and the black line is the corrected version. And the colored boxes here indicate whether or not the chi-squared value was shifted up or down. And so you can see here when you shift the chi-squared value, the critical chi-squared value up, that actually elongates and raises, like, I guess technically lowers your confidence of that. And then the red area kind of brings it in and puts a harder constriction on it. And so when we did the Feldman-Cousins process, we actually had to do it in two different ways. So we had to do what's called conditional fitting and non-conditional fitting. And so when you do a Feldman-Cousins run and you generate a pseudo experiment, you have to fit that pseudo experiment twice. You fit it once without constraining your parameters, and then you fit it once where you only constrain your not nuisance parameters. And you constrain the not nuisance parameters at your the bin point that you're at. And so when you do delta m squared 3, 2, though, there's a further choice you have to make when you do the best fit. So if you do a conditional fit, you are restricting delta m squared 3, 2 to stay within one mass ordering specifically. But if you do a non-conditional fit, you actually release that constraint and allow delta m squared 3, 2 to flop between negative and positive. And you could see how that affects this. So the inverted ordering conditional fit, the shaded region there is the actual Feldman-Cousins corrected 1 sigma region. And so under the inverted ordering, if we don't let it flop to the normal ordering, we actually get a range. But if we do let it flop, then we actually lose our 1 sigma region for this because it chose the normal ordering basically. And so, and this is kind of what we mean by conditional versus non-conditional. And it's important because you kind of get to see how you the removal of the 1 sigma range, I think, is very interesting because it's saying it's just another way of saying that we prefer the normal ordering, but without actually doing that. And so, yeah, this is just how the hashed area is the Wilks theorem assumption for 1 sigma, and the colored area is the Feldman-Cousins corrected. And you can see, so this is delta CP normal ordering, and you see we get 2 disjoint ranges, and this is showing us that 1 pi and 0 pi minimal delta CP, like CP violating phases that we prefer. And so without Feldman-Cousins, we actually don't get that disjointed range. We only pick up the 1 range. And so, and the Bayesian results also showed this disjointed range. So it's another indicator that we had to do Feldman-Cousins. And so how can we get the mass ordering sign from this information though? So using the Feldman-Cousins infrastructure, what we're able to do is determine, again, what I said, the rejection significance of the inverted ordering. So when we did it both with these Diabet constraints, but the way we did it is we generate pseudo experiments at the observed best fit delta m squared 3, 2. And we fit these pseudo experiments twice, but instead of fitting them once for the best fit and once for the constrained fit, we actually fit them both constrained, but assuming normal ordering and inverted ordering. And so you generate a pseudo experiment at our best fit point, and then you basically ask, okay, well, how likely is this experiment to be in the normal ordering or inverted ordering? And then we calculate that difference and count how many, like get the ratio of those, and that gives us a p-value, which you can turn into a rejection significance. And so this is a graphical display. So this shows the difference between the inverted ordering and the normal ordering chi-squared values of the pseudo experiment, and the red line there is our observed value. And so we're asking how many of our pseudo experiments that we generated are more extreme than our observed value. And that is basically the number of pseudo experiments that agree with the inverted ordering. And so then we could turn that into the rejection significances, which you see there. So for the reactor 1D was about a 1.4. So it should note these are weak rejections. They are rejecting, but it's not very strong. And so to do this, when I say generate many pseudo experiments in each bin, I mean like hundreds of thousands of Monte Carlo simulations that you then have to run a full fit on 50 parameters and then another full fit on only 48 parameters for each of them. And that is very computationally expensive. And so the way we were able to accomplish this is through parallelization, obviously, and we were able to use the Perlmutter supercomputer at NERSC. And so the NERSC has this Podman HPC containerization software, which we were able to basically port in a bootleg version of NovaSoft and Scientific Linux 7, which was not easy. And because we had to use modern MPI with the old software. And so the issue with the costs is that as you get farther out on the plot that you want to correct, the cost of the number of pseudo experiments you require blow up. And so, for instance, if we wanted to compute, that outer edge out there, you're looking at 10 to the power of 40 pseudo experiments. Whereas if you just are focused on this, like that 1-2 sigma region in there, it's much lower amount of pseudo experiments. And so we utilized like 13,000 CPU cores at a time. And even still, by doing that for a couple weeks, we weren't able to correct the full plot. It was just we didn't have enough hours. And I don't think we could have, even if we did. So we tried to think of a new way to fix this efficiency issue. And something that we found was known as it's importance sampling. So with importance sampling, instead of generating however many pseudo experiments in each bin that you require, you generate a fixed number of pseudo experiments in every bin. And then you fit those, you do a best fit for all of those, but then you use that same pseudo experiment and you fit it in each bin that you need correcting. So you basically get to reuse the pseudo experiment. And so instead of having to do best fits for every bin for all of their pseudo experiments, you do one set of best fits and then another smaller set of constrained fits for the whatever bins you're interested in correcting. And then after that, you have to weight the resulting fit value based on the original bin that you pulled it from. And so basically what this ends up doing is it vastly lowers the number of fits you need to do at higher significance. But the trade-off is that you actually end up having to do more fits at lower significances. And so in this plot here was a preliminary test I ran where I was able, so the red dots are the traditional Feldman-Cousins delta chi-squareds. And the unweighted mixture is that blue. And then once I applied the weight, it hit the green, which is almost exactly with the traditional Feldman-Cousins mixture. So proof of concept, it works. Unfortunately, in the case for NOvA, it failed to sufficiently reduce the computational time because we still have to fit it a lot. And at least for the NOvA 3 flavor analysis, the area of real interest is not out at 5-6 sigma. It's really below in that lower significance range. And so we actually would end up spending more on the important stuff just to spend less on the stuff that nobody cares about. And so it ends up not being a feasible approach. Now, the next use case that it can be is for the sterile neutrino search, which is also, NOvA also has a sterile neutrino program where they are searching for a fourth neutrino flavor, basically. So with that one, their area of interest is way out. And so that, I think, is going to be a good place for this to go, but there's still work to be done on that. But at least the proof of concept works. And then I didn't do my summary slide. Sorry. All right, that's it. Questions? I blasted through that. I thought I was going slow. Yes. I mean, if they want to do a frequentist analysis, yes. But I doubt it. I doubt they're going to. I think they're probably just going to stay. The undertone here is that the Bayesian analysis didn't have to worry about this. So my personal opinion is that we should just do the Bayesian analysis because this was very resource intensive for something that they didn't have to do. Oh, yeah. Oh, there. Sorry. So it has to do with the cyclic nature of, at least I'm fairly confident it has to do with the cyclic nature. This is a kind of a simple example. I think a better one would be the sine squared 2 theta 1 3, where so this one is all right here, but there are plots where it's like it wraps around the edge, and I think that that's a better image of why it fails. Um, but it's the cyclic nature that causes this non-ellipsoidal distribution. Now, as to why it needs to be ellipsoidal, I don't know. Yep. So there is a matter of fact uncertainty, but it's not strong. Say again. How sensitive? Could you sensitive to, as in, I'm not sure I understand the question. I'll talk. Yeah, find me after.
So I think some of us are, familiar with the NOvA experiment and have gone through this a few times. For those who've never really heard about Feldman-Cousins, is there a simple example that doesn't have 70 systematic uncertainties to just kind of, that, do we have like a toy example that can be applied to explain it?
There is. I don't have it actively available. It's actually I can. So a while back, I found that during one of the NOvA collaboration meetings, somebody did a tutorial basically, and they used a very simple toy example. It was about height, like the yeah. But I don't have it actively available. But I should probably. So.
If you want to dig it up and append the slide, we can make it available to anybody.
Yeah, absolutely. Yeah.
Right.
Yeah, because it is a very good tutorial, honestly. I mean, I watched it a lot.
What a cat.
Yeah, I don't know. Yeah, I guess he doesn't like cats because he had a dog. I get it. I don't like cats either. I am allergic to cats, is all. I like cats, but I love my dogs. Yeah, I hope not. Um, I don't know. I doubt that they'll let it go, to be honest with you. But uh, it's gonna take. So now that there's a lot of moving parts here, but the image that we used at NERSC for this was really a Frankenstein monster that shouldn't exist. Because I mean, we had to. This is going to get a little too. We had to install a new version of glibc, and then whenever we wanted to run our program, we had to set that as the main one, which meant you broke every other command. So you couldn't ls, you couldn't cd, you couldn't do anything. It seg faulted everything except for the command that ran and so it was like a nightmare. And now we're moving on to AL9, and so there's a whole extra layer of complexity that I don't think is worth. Again, this was very resource intensive for not much. Yeah, and I think that environmentally wise and cost effective wise, I don't think it's worth it. But I should probably stop saying that because I did my work on this. I don't think so. In fact, I think the more data we get, the less important this becomes. Yeah. Yeah, and that's a good point too, because I didn't really get into this, but the differences that we had for this analysis between the uncorrected and corrected was far less than the differences in the past. Because again, that large sample size you really start to make up for the bad parameters and stuff like that. Yeah. Yeah, so yeah, if we can get a lot of exposure, then I think we'll be good.
Let's thank Andrew one more time. Andrew will be around for the rest of the day.
Yep.
He's down in the guest office, room 9 downstairs. If you wanna, room 8, thank you, downstairs. If you wanna stop in and chat about statistics, he'll be available all day.